All right, let's have a look at this review problem. And we'll just go over this a bit. If you're watching and working along, what I suggest you do is pause the recording here and there so you can work on things. I think it's a lot better for you to do them on your own and kind of check what's going on here than it is just to watch what I'm doing here. Okay, so this is a review problem. It's the 3D review problem. It's available in the Moodle page downloads. Okay, so it's in the homework downloads is where it is. So what we're going to do here, and let's see, this thing is called 3D Review Problem 2014 in the homework downloads. Okay. So what we're going to do here is we're going to look at this rod here. It's attached at A. We've got a cable that goes from B to C that pulls on the rod. We've got the coordinates here of the different points, and what we have are some specifications for the shaft there, AB. It can handle loads of 12,000 newtons compression, 3,000 newtons tension, 6,000 newtons of shear, and 22,000 newton meters of moment. And if we apply this force here, what we'd like to know is, will the shaft fail? So we want to check and address all the cases, show your work. Okay, so that's the main part of this problem, is to do that. So the first thing to do is to come up with the coordinates of A, B, and C. So based on these dimensions, come up with those coordinates. All right, so you could pause the recording here and give that a run, and then we'll have a look at what you ought to be coming up with. All right, so let's have a look at what those coordinates are. Hopefully you've tried to find those, and here's what we've got. So negative 2.4, 3.0, and 3.6 for C. So there's negative 2.4 in the negative x direction. Right there. And then we've got 3.0 in the y and 3.6 in the z. So that's for C. For B, we've got 0.9 in the x, 1.6 in the y, and negative 2 in the z. And for point A here, there's nothing in the x. There's no x dimension to point A, so its x value is 0. And then we've got 5.8 in the y, and then a negative 0.4 in the z. All right, so that's the first thing to do. Now the second thing to do is to find the force vector from B to C. You've got the force magnitude, you've got the coordinates of B and C, so you should be able to work through that and find the force vector from B to C. So why don't you give that a run, and then you could, well, I would pause the recording here, give that a run, then after you've got it, check back in on the answer here. All right, let's have a look. So there we go, we get RBC, so we take, remember, to get RBC, we take RC minus RB. So RC is negative 2.43, 3.6, minus RB, so minus 0.9, 1.6, and negative 2. And then you just subtract off the like components, and you'll get the position vector from B to C, negative 3.3, 1.4, and 5.6. Take the square root of some of the squares, you get the magnitude of RBC, divide through by that, and you get the unit vector from B to C, and then multiply that by the 5200, which is the force magnitude up here, and you'll get the force vector, negative 2581, 1095, and 4380. All right, keep in mind, if you're, you might have a slight variation from my numbers there. If you round it differently, that's not a problem. All right, so that gets you the force vector. So the next thing to do is to figure out what's going on with this line. So I would go ahead and get a position vector between A and B, and I probably would find a unit vector for that also. So again, you could do that for AB or BA, whichever one you think is better. Find a position vector and a unit vector. And you could pause and give that a run, then and see what you get, and then start the recording up again and see what we got here. All right, there's the vector from A to B. So RB is 0.9, 1.6, and -2. RA is 0, 5.8, and -0.4. So do the subtraction, you come up with R from A to B. 0.9, -4.2, and -1.6. Right there, square root of sum of the squares gets you 4.58. Divide through by that, you get the unit vectors. So what we've got there is the position vector from A to B, and then the unit vectors, and I got both unit vectors. UAB is 0.196, -0.916, and -0.349. UBA, meaning the unit vector from B to A, is the negative of UAB. So you can turn these vectors around easily enough just by taking the negatives. All right, so we've got a position vector and a unit vector. All right, so what you want to do next here is find the compression in AB. All right, now notice that BC is pulling from B kind of in the rough direction towards A. So I think we're going to have a compression in there that goes from B towards A. So if you use the BA vector, you'll get a positive answer. If you use an AB vector, you'll get a negative answer. So I'd use the BA vector because that's in the direction of the compressive force. So why don't you pause and find the compression in that shaft there, and then start off the recording and we'll have a look. All right, there's the compression. Okay, so to get the compression, you take the dot of the force vector with the unit vector. Okay, so we got the force vector from B to C. We dot it with the unit vector, and I use the unit vector from B to A. That way, when I run the dot, I get a positive answer. All right, now when you do the dot, you take the like components, you multiply them together, and then you add up the products. So the dot product is a scalar, 3,038 newtons. All right. Now, had you used the unit vector from A to B, you simply would have got a negative 3,038 newtons, which would be fine. It's not a big deal. Okay. No worries there. Okay. So the magnitude of the compression in BA is 3,038 newtons. All right, why don't we find the shear next, okay? And I actually just had that projected. I forgot I had it there, but why don't you pause here and see if you can find the shear magnitude in that shaft, AB, okay? All right, now to find the shear, the relationship here is that the shear is perpendicular to the shaft. So the compression runs in the shaft. The shear is perpendicular to the shaft. So that relationship is something like that, okay? Now they're at right angles to one another. And so there's a vector relationship that the compressive vector plus the shear vector would equal the total vector, okay? So that's the relationship here. So if you want to find the shear vector, what you can do is take the total force and subtract off, in this case, the compressive vector. Now, if that will get you a vector answer, now if all you want is a magnitude, you can just use the Theorem of Pythagoras. So what I would do here is I would take FBC, square it, take away F compression, squared, take a square root, and then what that'll get you is the shear magnitude. So that's how you could find the shear magnitude, which is really all we're looking for in this problem, because all we really want here is just we're comparing our answers of tension, compression, and shear to the allowable values for the specifications for this shaft. So all I need is a magnitude. So I just go ahead and do that, and that's shown there on the bottom. So 5,200, which is the magnitude of FBC squared, minus the magnitude of the compression, the 3,038 squared, take a square root, you get 4,220. That's the shear force. Okay? So All right, so that's the compression and shear. Now, a couple other things on this is, first off, when we're doing this, when we found the compression, our approach for doing that was to use the unit vector for the shaft. And the reason for that is that we don't really want the length of the shaft in our answer. See, that if we just want the projection of FBC on the shaft itself could be any length. That would not affect the answer. All we're really looking for when we find that projection is just basically the cosine of this angle right here times the 5200, and that's what the dot product gets us. Okay, the length of that shaft, the location of point A, is not important in that calculation. So what I want to do when I find a compression or a tension, which is an axial force, what I want to do there is dot the force vector with the unit vector for the line that I'm projecting onto, which is AB or BA, either one. So there are the unit vectors. And the reason, again, is I don't really care how long the line is. I just care about the angle between the line and the force. And that dot product will automatically generate the cosine of that angle times the force vector, and then in the case of a projection, times the unit vector for the line. And that'll get me that shear, or excuse me, not the shear, the compressive component there. Okay. All right. Now, the other thing I'll mention here is we're given a specification for the shaft for how much tension it can handle. But you don't really need to use that at all. You don't need to analyze that. Okay, the tensile strength is 3,000 newtons. So when this shaft is manufactured, they give it values of how strong it is in these different modes: tension, shear, and moment, and compression. Okay, even though they've told us what the tension is, we don't have any tension in this situation because we're pulling with that cable from B to C. So there isn't any tension in this, so we really don't need to worry about that. It's not going to fail in tension because there isn't any tension applied in the shaft. All right. All right. Now the next thing to do here is to look at the moment. So why don't you calculate the moment at A that's caused by FBC. So you could pause the recording and give that a run, and then we'll check back in. All right, now the moment is the position vector from A to B. A is the point we're taking moments about. B is a point on the force, on the line of the force. So we take RAB and we cross it with FBC. Okay. Now that's a cross product involving both vectors. The position vector goes from A, the point about which we're taking moments, to B. So that's important, okay? It's going that way. It has to be AB. You can't really use BA to do the cross product. If you do, you'll get the negative of the proper answer. So you want to go from, this case, from A to B, because you're taking moments about A and you're going to the force at B. You then cross it with the force vector. Okay? So you have the position vector first, crossed with the force vector second. Okay, the position vector, again, I think of it as being a wrench. I've got the head of the wrench on A. The handle of the wrench extends back to B. Now notice that I'm using a position vector for AB. I'm not using a unit vector like I did with the dot product. I'm using a position vector. The reason is the longer that distance is, the farther it is from A to B, the longer the wrench is, that will increase my moment. So the length of that line affects the magnitude of the moment, okay? So I want that length in there in the calculation because it affects what the moment is. So I do not want a unit vector here. I want an actual position vector. All right? And then the other thing on this is it's R cross F, not F cross R, but R cross F, okay? So that's how that works. So you can do the cross product in many ways. The formula is right on the formula sheet. I use determinants because that's how I learned it. However you care to do it is fine with me. So we can go ahead and run that cross. So to get the x component, you cross off the first column, top row, and cross what's left. So negative 4.2 times 4380 minus negative 1.6 times 1095. That's the I. Then what we can do is we can cross off the middle column, top row, cross what's left. So 0.9 times 4380 minus negative 1.6 times negative 2581. That's the j component. The j component is always subtracted. And then the last thing you do is you can get the k. So what you do there is you cross off the last column with the top row, cross what's left. So 0.9 times 1095 minus negative 4.2 times negative 2581. And that's the j there, or excuse me, the k. So you just multiply all that stuff out and add it up, and you get the MA vector, negative 16,644I plus 188J minus 9554K. That's a Newton meter on that. Moments have force and distance in them for units. To find the magnitude of that moment, you take the square root of sum of the squares. All right, so there's our run through on calculating the axial force, which in this case was compression, the shear, and the moment. So just compare those to the allowable values and then see if this shaft will fail or not. Now I've got a little bit of a part 2 there. And the part 2 asks the question, what can the maximum force in cable BC be before the shaft fails? So how high can you have this force go until the shaft will exceed one of those values, one of the specs that are shown in the problem statement, in which case the shaft would fail. So that's part 2, and you can work through that and see what you get on that. Okay, so this is just meant to be a bit of a review for the for the midterm, which is on Monday, and give this a run. I'll have you turn it in next week sometime, so just get this filled out and good to go. See what you can do on part 2. If you have questions on that, I'll take them. All right. The other thing I would advise you for this test is look at the formula sheet you've got. I'll give you a new formula sheet for the test. Have a look at what formulas are used and where they are on the formula sheet so that when you're looking at this stuff, you've got it, okay? So what we've got here is where it says projections and moments. So I've got FAB parallel to FBC, that's on the formula sheet, equals FBC dotted with U, or actually I've got FAB dotted with UBC in the formula sheet. That's what it says. Now in this case we use different letters, but the concept was the same. So this means FAB parallel to FBC, which is an axial force, which in our case was compression. And our force went from B to C, and our shaft went from B to A. A little different than the subscripts used on your formula sheet, but that's okay. Those could always vary a little bit. So that formula is right on there. Okay. Similarly, I've got the formula for moment, which is simply that M is R crossed with F. That's a vector operation. Then I have the determinant form and the actual formula for doing a cross product. So that's on there as well. So just have a look at those and just understand, what sort of information you'll have on the formula sheet. And so you just know where it is and what it looks like before the test.